Awesome. Thank you very much, Bobby. As Bobby said, my name is Jacob Smith. I'm a staff engineer with the ARM group. My boss, Brian Bonner, took over this project. What year did you get this from, Terry?
2016.
Okay. So
about 8 years.
So 8 years on the project, and kind of have some deliverables we wanted to share. So a little bit about the Mosquito Creek watershed. Here's a kind of a map here of the West Branch Susquehanna River. There's Mosquito Creek itself. So Mosquito Creek, the watershed itself, encompasses, it's a tributary of the West Branch Susquehanna River. It encompasses Elk, Cameron, Clearfield counties. It is a 63.9 square mile watershed, and it is 90% public land located within the Pennsylvania Wild. So this is a prime area for recreational benefits if restoration is completed. And it was once considered a world-class wild brook trout stream. People traveled from all over the area to fish. Within the 1980s, they started to see degradation, mainly by local sportsmen, including the Mosquito Creek Sportsman Association, and they saw fish kills and lowered fish counts throughout the watershed. So what was the problem they were seeing? So they started getting these fish kills, and they stocked some areas of the watershed, and they saw that the stocked fish that they were putting in were not staying, and the native fish and the wild fish that were there were disappearing as well. So they found a very low pH value within this stream, and it was coming from acidic deposition. So I think most of us probably know what the cause of acid rain, more commonly known as acid rain or acidic deposition, is. You have upwind sources that burn material. They produce nitrogen oxide, sulfur oxides. Those combine with water to produce nitric acid, sulfuric acid, and that rains down on your watershed and you get an acidified runoff. Within a lot of watersheds, you'll have a natural or a native buffering capacity, and here it's referenced as an inherent alkalinity. This would be native limestone or other carbonates within the stream that would buffer that acidity coming off. So in an area where you do not have this inherent alkalinity, to balance this out, you need to add alkaline material to have your restored stream section. And I think this is a really good document that I found. It's from about the 1980s, 1990s. I couldn't find an exact date on it, but during the 50s and 60s, Mosquito Creek was locally known for its abundance of large wild brook and brown trout. Right there is right from the Fish Commission, it's a very powerful thing. But what they saw, was that, I think the end here, water quality has changed. An examination of historical records reveals a recent disturbing trend. What would that disturbing trend be? This shows it. You can see in the beginning of water quality samples referencing pH and total alkalinity. In 1957, still a pH of 6.7 and a total alkalinity of 30 milligrams per liter. Pretty standard for our, that region there. We're not going to have very high alkalinities or very high pHs just due to the sandstone geology. When you get down to 1980, we're getting 4.6, 4.8, 3.9 in 1981, and a total alkalinity of 0.5 and 0. Those alkalinities were likely 0 even yet, if not due to the acidity, so it would be considered a net acidic stream. So the area was considered chronically acidified. This just shows it here. I think it really graphically shows the issue. I mean, pH and alkalinity were both going down greatly within the watershed, and saw that through multiple samplings and also fish kills and lowered, reproductive amounts within the watershed. So what was the historical items that were taking place for this? So there were several local sportsman clubs, mainly the Mosquito Creek Sportsman Association, that worked to install soda lime dispensers, and most recently limestone sand dosing. I know some other people at this conference have talked about their watersheds groups doing limestone sand dosing. It's very effective, and all these systems worked well to increase the pH and add some buffering capacity to the watershed. But there's one major problem to it. All of these systems incur substantial operational expenses and require a lot of upkeep to keep them going. Show of hands, how many people in here have carried limestone to diversion wells or something like that over the years? It's an ongoing maintenance that you need to do, and it often ends up failing due to that. So what was the goal of the Mosquito Creek restoration plan? So the goal was to reverse damage that had been done and improve water quality throughout the watershed. And this was done by increasing the buffering capacity to limit pH swings, both chronic and episodic. And it was determined through multiple studies that the largest impairment to the watershed was chemical, and that was the underlying problem, the lowered pH values. It was not a habitat loss or anything like that. It was a chemical lowered pH in the watershed. And since they had been doing limestone sand dosing within the watershed, Gifford Run, the largest tributary to Mosquito Creek, they had ideas of what did they need to get to sustain a wild trout population, because they were holding fish within this. And they found that 20 microequivalents per liter at normal flows and 5 microequivalents per liter at high flows held wild trout. What's really important is that these parameters needed to be met at all times. If you didn't do that, you would end up having all your sorry, I lost my words there. All of your benefits that you had created would disappear. They would be lost. So to look at how to restore an acidic stream, you need to classify acidification of that stream. And these graphics work really well. If you plot A and C, which is basically your buffering capacity of your watershed, it's just a different way of showing it, and your flow rate over multiple samples, you can get a line there. And your neutrality threshold is when your buffering capacity is at 0. So you're at a net 0. Any acid you add to that will go to lowering the pH rather than using up the alkalinity within there. So we have 3 classifications. A sustainable acidification is a stream that this neutrality threshold is above the 95% confidence interval. This would be your standard streams within northern Pennsylvania that are not known to be acidified. So you go there most of the time, you're going, all but the highest flows, you will have fairly good pH values and a buffering capacity to them. If we look at a stream with a neutrality threshold in an episodic area, this is where you have above a base flow, so kind of more of like that bank flow, bank full amount, you get that your 0 threshold there. So any extra acidity added to it will lower the pH. And this is what we're seeing more and more today. As acid rain or acidic deposition has improved throughout the United States, and including north central Pennsylvania, we see a lot less of it, a lot more of this rather than chronic acidification. Now, chronic acidification is exactly what it sounds like. This is when you go to the stream at a base flow, so a low flow time, you will have an acidic condition. So this is when the base flow buffering capacity of the stream is equal to the base flow acid loading. So how did we go to, how did we want to restore this here? So we wanted to utilize a holistic watershed approach and go from the top down. When you do the top-down approach, you end up getting the most miles of stream. Because of acid rain, you don't have a specific loading point as, like you see with an AMD discharge. So the issue starts in the headwaters and can go throughout the entire stream. So to get those acidic loadings or the entire watershed restored, you have to start at the top. We wanted long-term commitment. Too many times I've seen projects that the long-term commitment is not there, and then you end up getting projects that go for a short period of time and end up failing or, due to that. We wanted to integrate multiple treatment systems. If you put all your eggs in one basket with one large treatment system on a watershed, if that treatment system fails, you end up, you'll lose all of your progress within the watershed. When you put multiple systems in headwaters throughout the watershed, you get separate areas that you can restore. And the biggest one is a low maintenance solution. Passive treatment, you want to keep this as low maintenance as possible. Passive treatment does not mean no maintenance though. Just because it says low maintenance, it's not no maintenance. Something I've always stressed and seen is passive systems. You need to still go out, walk the site, look at it, see if there's an issue going on with it. And then funding sources, something I'll talk a little bit more at down here. So when choosing treatment technologies, I think of a scale here and which way we want to look at. So you need to balance your upfront cost with long-term operation and maintenance. You can have systems like diversion wells have a much lower upfront cost to install, but they require a long-term commitment and long-term operation and maintenance. Oftentimes these maintenance, due to funding issues or labor supply, you're not able to continue the work there. So these systems prioritized a larger upfront grant-funded source of money to buy all their buffering capacity at the beginning in designing a passive treatment system. So this is where we talk a little bit about the actual systems itself. This is a picture of we have 4 passive treatment systems within the watershed. We have Pebble Run, was built in 2004. The Duck Marsh was built in 2004 as well. Lost Run was 2014, and then Ardell Road was 2001. And these are standard vertical flow wetlands. You guys probably all are familiar with them. Very simple. You have a 3-foot layer of high calcium limestone, a 2-foot layer of mushroom compost, and a 1-foot freeboard on there, utilizing an agri-drain outlet and a 100 by 100 basin. The intake systems on these are what's a little bit interesting. They build a check dam across the stream to get a water level control here. And what they had done at the time was put a pipe on the backside of it that goes to an agri-drain with an orifice. We want to treat 100 gallons per minute. The largest problem with a vertical flow wetland is if you drive them too hard, you'll have using of the compost or settling of the compost. So when you drive them at approximately up to 140 gallons per minute at a very peak flow, you don't have those issues there. And these work to increase alkalinity out of the back end of them. They're also known as a SAP system, so if anyone's heard of them, successive alkalinity production system. The reason the compost is there is to create an anaerobic environment where metals do not precipitate onto the limestone. This area does not have the high metals that most of the discharges you guys are treating are encountering have. So while the compost may not have been completely necessary, it also increased, with creating an anaerobic environment, increased partial pressure of carbon dioxide onto the water, dissolved more limestone into it, and you get a higher production of alkalinity out of them. The goal was to just create as much buffering capacity for a chronically impaired stream as you could. Now, episodic treatment, is a little bit different. These are the streams that you have at a low flow or a base flow, you don't have a problem of acidification. So you don't need to add buffering to them at those low flow events. When you want to add buffering capacity is at a high flow event, a bank full event, storm events. So what they came up with was a high flow buffer channel. And this was used to treat episodic high flows. People that have done limestone sand dosing, you might have noticed that you get a smothering of macroinvertebrates downstream from that limestone sand dosing location. A lot of those fines that come out of that limestone tend to smother out the macroinvertebrates within that section. So this reduces that, and it also reduces the total limestone sand used. If you think about it, you're only adding limestone sand to the watershed at the times it's absolutely needed. One of the comments I had gotten from people on this type of design is that the contact time is not enough through the channel. Through what I have found in seeing these systems work is that you actually get more of a mechanical abrasion of the system that's releasing that in there. It's not so much the chemical dissolution, but more of the mechanical, breaking up the fines and getting them within the watershed. And this is one that has been within the watershed for 2012 it was installed. So we've had very minimal maintenance to it. The vertical flow wetlands that we had, the 4 systems, we had one intake that we had to work on, but the rest of them have over 20 years of continuous monitoring and have been working. So is it working? Yes. Fish and macros have returned to much of the Mosquito Creek watershed. From State Route 879 to the headwaters is now listed as natural trout reproduction. That's a huge, huge improvement. Prior to this project, they were not seeing many trout within it. Not only do you have the wild trout, but the Sportsman Club has continued stocking Gifford Run, and their fish are staying within the section that they're stocking in. And kind of the performance of it, so Ardell Road was built in 2001, and we now have almost 25 years of continuous operation of that. They were built with a 20-year expected lifetime of the compost. The compost will degrade over time. It rots, and that's actually what uses up your oxygen within it. There's enough limestone for approximately 80 years at the designed flow rate. Likely that is higher because it's not, in a dry time like now, when I was up there a couple weeks ago, the systems were not flowing because the streams were at the lowest part. So we're seeing around 80 milligrams per liter production out of these systems, which is very close to the designed values. So each system on average is producing, obviously the intake water, the more acidic your intake water is to the system, the more dissolution of limestone you're going to have. So Pebble Run, which is my favorite system out of it, has a very acidic intake water. So that one produces the most alkalinity per year. We get about 9 tons of production out of these systems, Pebble Run. It's closer to, the other ones are between 6 and 7 due to having a little less acidic intake water, but still really good production within them, 25 years down the road. So now I'm going to take a look at some streams that you guys probably all, have seen. How many of you guys have seen streams like this? Pretty much everyone, right? That's why we're here at an AML conference. I'm sure we've all seen streams like this though, right? Which of these streams do you think is considered impaired for low pH values? I want someone to take a guess at this. One on the right? You were right, it is, but they're actually both impaired. This is both the same watershed in Schuylkill County. Yes. So obviously, the photo on the left is a bit of an exaggerated photo of that watershed there. Wayne's familiar with where that photo is taken. It doesn't look like that nowadays. It's much better, but it still does have it still is an acidic stream there, but the upper section of that stream does not have the mine seeps that the lower section has. So when I was out there as part of a mitigation project, we had the opportunity to do on-site mitigation for an expansion. And going through this, we saw that the stream, Upper Swatara Creek, located on the property, had a very low pH value in it. If we take a look at here, I did titrations and field pH measurements on this. So the proposed intake that I was looking at, you can see in December of 2024, pH of 4.39, a negative ANC. So this stream right here, this was at a base flow, would be considered chronically acidified. You go downstream and you see that we get a little bit better pH, up to 6.5, but still fairly low buffering capacity. That's to be expected in this type of stream. Beginning of 2025, still chronically acidified. In May, chronically acidified at the proposed intake. So we have a similar impairment to the Mosquito Creek area there. What we were able to find was that we had long-term performance data from the Mosquito Creek projects to actually classify, if we were to build a system here, how far an improvement downstream would we reach our goal, right? So I knew the loading long-term real-world data from the Mosquito Creek systems. I knew the deficit within the stream, and I created samples and a mass balance to go down the stream. So I knew at these points, if I installed this system with the expected loading that I saw, would I meet the goals that I set forth in the Mosquito Creek project to have a wild trout fishery? And that was the goal of that. And we looked at long-term operations from the Mosquito Creek projects. There was a couple things. When you implement something for the first time, you go 20 years down the road, there's small things you can learn from it that we implemented within this. So now this gets a little bit of the map portion of it of, why is this guy talking about acidified streams from acid deposition at an abandoned mine lands conference? So show of hands, how many guys in your watersheds have streams that fit the chronic acidification that I described there? You go there and you see a lowered pH value all the time. Pretty high values there. So we know this is an issue. So I overlaid the 319 impairment of streams from straight acidic deposition onto the state. And we can kind of see it pretty much covers the coal regions, right? We get the anthracite region. We get a little bit up here in this northeastern area that's not so much, doesn't have as much coal, but then the bituminous region, we get that. So I looked at, there's something that's putting all these streams together. Why are they together? And if I look at the late Paleozoic era rock, the surface rock within the state, we see that we get a really good overlap there. This time in geologic history, Pennsylvania was not a shallow sea, it was a swamp. This is basically the time frame that coal was produced within Pennsylvania. So this includes the Mississippian, the Devonian, and the Pennsylvanian time frames. And if I overlay other streams that are impaired for not just straight atmospheric deposition of low pH, this could include streams that have atmospheric deposition and also may have a small metals in it from really low pH, we can see this really closely counters that. And we see that the coal fields in Pennsylvania could very well be a place to implement these technologies. These are, upon the querying of this, I went for different parameters that were very similar to the Mosquito Creek watershed, and also some watersheds that I knew were impaired, including the Upper Fishing Creek watershed and the Bowman's Creek watershed, that are known to have issues from acidic deposition that are not just straight acidic, listed under 319 as acidic deposition. So many streams within the coal regions are susceptible to acidification due to the native geology there. And if you're only looking at direct AMD discharges into the waterways that you're working in, you may be missing both acid loading and you may be missing areas in your watershed that you could restore. You could have a wild trout population. The cost to restore a stream from acidic deposition has been found to be much lower than straight AMD. When you're designing these systems, you don't have to deal with metals. And as you guys that design these systems, you know that sludge handling, the stone imbrication, and the issues that come along with metals is a great cost to the treatment facilities. And you also don't need to build as many ponds to settle the metals out here. And you can see this is actually a picture of this spring that Brian took of the high flow buffer channel. So the stream had not gotten to its bank full capacity yet, but you can see it's getting elevated and we're starting to get some water go into that. So, if we once we start getting a little bit higher flow than this, that water will actually be going in there, dissolving that limestone, picking up fines and taking them downstream without smothering the macroinvertebrates within that stream. A couple things to note when looking to do this type of restoration. You're not limited to the location that you're placing this system. Where an AMD system, you usually have a discharge there, and you have to center your system around that discharge or pipe that discharge to where you're looking to design that system. Well, with this, anywhere on the stream in the headwaters, you can place that system. As long as it meets the site constraints of a fairly flat site, fairly easy access to the stream, you're able to put these types of systems in. I also looked at for our system we designed here, this is one of the intakes from Mosquito Creek. This is well over 10 years of sedimentation into the intake. Well, the intake was still working. That stream is Pebble Run, has a really high bed load to it. You don't name a stream Pebble Run without being full of pebbles. So you get a lot of sedimentation dropping out, and it does offer a little bit of an issue with getting it in. Streams don't like to be put into a pipe. You have a lot of dirt in streams, a lot of leaves. They're messy, right? They do not offer a very easy engineered way to get water out of them. So with the next system that we designed, I looked at using a Kawanda intake based on actually some other people's recommendations, as leaves tend to get into we're getting into the orifice of the Mosquito Creek systems. And we wanted to pass this gravel. So I actually designed the intake to have the gravel go over top of that and go downstream, passing the bed load at a really high flow event while still allowing me to take water off. And these Kawanda intakes, they're manufactured for small hydroelectric, like homeowner type hydro facilities. So they're off the shelf, they're low cost, and talking with them, they have a really good following from those guys that like them. So, conclusion, the Mosquito Creek project has had significant long-term water quality improvement. The project has also served as a trial run for watershed restoration throughout the state, including the Upper Swatara Creek. And some of the lessons that I think are really important that came out of this that would go into design of any passive treatment system, not for just acidic deposition or AMD, is that low maintenance does not mean no maintenance, and inspections are important. And I will live and die on, intake design is the most important item within passive treatment systems. Time and time again, that is often the cause of these systems not working or failing, is because of that. Little quote here from John Sayers, who wrote a book on the Mosquito Creek, the Sportsman Club. And I think it kind of really speaks to it. If the current environmental problems of acid rain and waste dumping were limited by science, there would no longer need to eye remote areas as ideal dumping sites. The Queehana Wilds was what once a dumping site for a lot of items, so I think it's a pretty powerful item. Any questions on this? Yes.
From looking at it, obviously Mosquito Creek, I'm fairly familiar with. I've fished up there before.
Mm-hmm.
It was a good fishery, and it went bad due to acid rain. I don't think it might be a coincidence that might fall in line with a lot of coal-fired power plants in that area. And those coal-fired power plants are going offline. Do you expect, or are you seeing just improvements just from those being removed, and not seeing nearly as much acid rain up there as we once did maybe in the 70s, 80s, or 90s?
It's a great question. It's twofold. So we are seeing a lot less acid rain in those areas. Talking to anglers in other watersheds locally to that, they've seen increased populations just based on, and those areas didn't have treatment done to them. So the areas that were untreated are seeing improvement. The Mosquito Creek watershed was hit very hard by acid rain, and because there was no buffering capacity, or very little to begin with, there's a lot of acidity that has leached into the soils, and you're just getting a lot of that residual left over from that. The values that I'm taking going into the treatment facilities, which obviously from there up is untreated, while that is better than what they saw in the early 2000s, they still are 4, 3, and 5 on a lot of them. So and that's at a base flow level. At a chronic, on an episodic flow, we still see those really big swings just from that loading that was already left within the watershed. But great question. Yes. So that was one of the major concerns was, at a lower pH, you're going to get aluminum distillation from the soils. We never got to that level. And I think now that the acid rain has improved, the samples that were run in the early 2000s, which was the worst time for aluminum loading, they didn't have that there. I haven't run aluminum samples currently, but I don't suspect that there's anything going into that. Mm-hmm. Yeah, so Terry Reitnauer, who had designed these systems originally and implemented them, he had looked at putting these in without limestone, without the compost on the end part there. The compost really seems to help with reducing that oxygen and keeping metals from precipitating out onto that. I don't have experience of these systems without the compost within them. I would be more worried about the metals precipitating and imbricating the limestone. While we have very, very low levels there, there's still some there that would imbricate it, I would think. Going back into the stream, you mean? Or so they ended up the first system, they did not implement a wet, like I call it like a buffer channel at the end of these systems to kind of let some of that CO2 drive off. In the next two systems, they did implement wetland channels at the end of it, which drove off a lot of that CO2 and just kind of you get a lot of like tannins really leaching out of that compost. So it kind of used up those tannins and allowed it to go back into the stream and just look a little nicer. That was the thought behind that. So the system I designed in Swatara Creek, we did put a wetland on the end of it to polish the water. I don't see any hurt in that, and it would kind of add some oxygenation back to that water before it goes back into the stream. Yes, Bobby.
Are you testing the water at the outflow of those systems is the op channel, or are you testing it in the mainstream? Because you're talking about it going bank full, and that's when episodic acidification is going to be going down, when the water's high. So if you're off channel, you're getting just a small percentage of what the overall, sort of push is on what's coming down the stream. Where are you monitoring?
The systems each have 3 monitoring locations. So at the intake weir, which you would be measuring the stream itself since it's an on-stream weir. At the outfall where where either the pipe enters the stream or where the wetland channel goes right to the receiving water, and then downstream about 100 foot below, about a mixing area there to understand what it is below the system and what you're actually seeing there. So you would be getting that. The vertical flow wetlands were installed on streams that were chronically acidified. So obviously at a higher bankful flow, you're going to see acidification yet. Now Gifford Run, which the high flow buffer channel was installed on, which is the episodically acidified one, the sample point is the same thing. Above the inlet for the high flow buffer channel, at the outfall of the high flow buffer channel when it's flowing, and then below about 100-foot mixing zone below that to actually show what the stream is at, below your confluence there. Yes, Bob.
When sometimes when we've installed passive systems on a viable trout stream, we get a lot of questions about temperature. What pluses and minuses of this? What do you know about how these systems affect temperature?
So earlier this year, I installed temperature loggers, the hobo loggers, above and below 2 systems. I put it above and below the 2, one with a buffer channel at the end of it and one without it to see if that made the difference. Sadly, with our low flows we had this summer, the systems weren't running through the hottest time of the year. So I didn't see a whole lot of, the systems weren't running when it would be most, susceptible to the temperature, but taking temperature readings above and below, I see very little difference to them. Actually, I've seen in the summertime, because the flows are much lower, and this is kind of a below ground grade system, the temperatures coming out of the system, out of them, tended to be lower than the intake temperatures. So for a trout stream, that's good.
Any other questions? All right, well, thanks, Jake.
All right, good. Off to a rough start at first, but I got in there then. Yep. So I had done this stuff in college, so I had a